All right, so the next law here is the combined gas law, where we're going to use the combined gas law to find the final pressure, volume, or temperature of the gas when changes in two of these properties are given and the amount of gas is constant. So here, we're going to be given 5 of the 6 variables, and we're going to go ahead and look at the combined gas law, in which there are actually 6 variables instead of the usual 4. So the combined gas law incorporates all pressure, volume, temperature relationships for gases previously studied. Is useful for studying the effect of changes in 2 of these variables on the 3rd variable while the amount remains constant. Amount meaning number of moles. So here's the combined gas law. Notice the top part of it, the pressure 1 times volume 1 is equal to pressure 2 times volume 2 was Boyle's law. And then volume 1 over temperature 1 and volume 2 over temperature 2 is Charles's law. And then pressure 1 over temperature 1 and pressure 2 over temperature 2 is the Gay-Lussac's law, the one we just finished. Right? So all those 3 laws are put together in the combined gas law. And no change in the number of moles of the gas. All right, so the properties held constant in this law here would be the first one, temperature and number of moles. And the relationship would be pressure 1 times volume 1 equals to P2 times V2, which is Boyle's law. And then volume 1 over temperature 1, keeping pressure constant and number of moles constant, you end up with Charles's law. And then keeping volume and number of moles constant, you end up with Gay-Lussac's law. Helium has a volume of 0.180 liters, a pressure of 0.8 atmospheres, and a temperature of 29 degrees Celsius. So right there you have 3 different variables describing 3 properties of a gas: volume, pressure, and temperature. At what temperature in degrees Celsius will the gas have a volume of 90 milliliters and a pressure of 3.20 atms? So notice there's 5 variables here, and the 6th one we're trying to find. So let's go and put this one up on the board. Okay, so volume 1 would be what? And when you read this problem, you have to decide that this is going to be a combined gas law problem, and you have to decide that you'll be using the combined gas law formula. So when you see the problem and you see the mention of the pressure, volume, and temperature in the same problem, and no moles, no number of moles, then you know it's the combined gas law, because all 3 properties of gases are in the same problem. So pressure 1 would equal to the 0.80 atms. Temperature 1 equals to 29 degrees Celsius, add 273. And then temperature 2 we're trying to find. Volume 2 is 90 milliliters. This has to go into liters. And then pressure 2 is 3.20 atms. Okay. Make sure you always write your formulas down first. And then plug in your variables, and don't put numbers into the calculator directly. It does not help. All right, so pressure 1, 0.80 atms. Volume 1, liters. And then temperature 1 was how much? 29 plus 273? (302 Kelvin). Equal to pressure 2 is 3.20. All right, the 2 is going to be 0.9 liters, and temperature 2 we're trying to find. So once again, you want to cross multiply. It's easiest to cross multiply with these problems too. 0.800 times 0.180 liters times T2. Times 30210. And then you want to isolate the temperature too, so you will divide both sides by the product of those two numbers, which is, so you can write them out. There, all this cancels. And this is going to give you the answer in Kelvin. And then you have to take away 273 to put it into Celsius. The problem asks for the answer to go into Celsius. So this part should give you 604 Kelvin.
Can you multiply it and then cross multiply? So you'll multiply 0.8?
Sure, yeah.
Okay.
Yeah. And some people prefer to do that. That way it reduces the numbers down to 1 for the numerator and 1 for the denominator. Any questions on this before we go on to another problem? All right, here's another one. I'm going to let you all work on it, and then I will show you the solution. All right, so our next law is called Avogadro's law, and this gives you the relationship between volume and moles. Use Avogadro's law to determine the amount or volume of a gas when the pressure and temperature are kept constant. What would you expect before we look at the law? Should volume and number of moles be directly proportional, or should they be inversely proportional? Volume and number of moles are directly proportionals. When the volume is 1 liter and the number of moles is 1 ml and volume is 2 liters, number of moles is 2 liters. Number of moles is 2 moles. Avogadro's law was formulated by Amedeo Avogadro in 1811. States that the volume of a gas is directly related to the number of moles of gas when temperature and pressure are held constant. So the relationship looks very much like the volume, temperature, and the pressure, temperature formulas we've been looking at. The volume of a gas is directly related to the number of moles of the gas. If the number of moles is doubled, the volume must double at constant temperature and pressure. If a 0.75 mole sample of helium gas occupies a volume of 1.5 liters, what volume will a 1.2 mole sample of gas occupy at the same temperature and pressure? Y'all want to go ahead and make a guess? If the number was exactly, well, actually the number is, no, it's not exactly double. So we're going to go ahead and put on the board number of moles. The first number of moles is 0.75, and the volume occupied here is 1.5 liters. The number of moles goes up to 1.2 moles. Then the volume should go up to how much? Let's see. Number of moles, 0.75 divided by 1.5, and then 1.2 divided by volume 2. So volume 2, once again you're cross multiplying just like before, and it's times the 0.75 moles. Numbers here are 1.2 times 1.5. we're looking for molar volume here. So 2.4 liters. And you can set it up in a chart like this, and then rearrange, and you should get your 2.4 liters. All right, the volumes of gases can be compared at STP. STP is standard temperature and pressure conditions. Standard temperature is exactly 0 degrees Celsius, which equals to 273 Kelvin, and standard pressure is 1 atm, which is the same as 760 millimeters of mercury. All right, so the volumes of gases can be compared at STP when they have the same number of moles. At STP, 1 mole of any gas occupies a volume of 22.4 liters, which is approximately equal to the volume of about 3 basketballs. So in this first balloon, you have 1 mole of helium, and its mass, of course, is provided, and the conditions are 273 K and 1 atm. In the second balloon, it's 1 mole of oxygen, 32 grams of which weighs 32 grams because oxygen is heavier, and then in the third balloon you have 1 mole of nitrogen, and of course its mass is 28.02, which is the mass of the diatomic nitrogen and oxygen. What does this tell you? Temperature and pressure conditions are all the same, and 1 mole of any gas is occupying a volume of 22.4 liters under those temperature and pressure conditions. This is telling you that the volume is dependent on what? What's common among these 3 balloons? The 1 mole, and 1 mole means 6.02 times 10 to the 23 particles. So the volume is directly related to the number of particles, and not on the size of the particle, or not on what kind of particle you have. When a gas is at STP conditions 0 degrees Celsius and 1 atm, its molar volume can be written as a conversion factor and used to convert between moles of gas and its volume in liters. And based on what you see on this page, 1 mole of any gas at STP, as long as the conditions are STP conditions, is going to occupy 22.4 liters. And you can write that as a conversion factor. So if you knew, as long as the gas was at STP and you had half a mole of the gas, of any gas at STP, then it would occupy half this volume. If you had 2 moles of a gas, which could be any gas, and the conditions were standard temperature and pressure conditions, then it would occupy 22.4 liters times 2. Does that make sense? Okay. All right, what's the volume occupied by 2.75 moles of nitrogen gas at STP? You know the volume of 1 mole of nitrogen gas at STP, and you can calculate for the 2.75 moles. So you start with the number that's given. When you're doing dimension analysis, you want to start with the number that's given, and then look for a conversion factor to cancel out the units that you started out with. So 2.75 moles. You're trying to find molar volume at STP. You know 1 mole occupies 22.4 liters, the conversion factor we just looked at. This and this cancels, and you'll have your answer in liters. And the answer is supposed to be 61.6 liters of nitrogen. Any questions? Okay. At STP, the density of a gas is calculated using the molar mass of the gas and its molar volume. You know density is mass over volume, and so it's going to be molar mass over molar volume. Balloons rise in the air because helium is less dense than air. Calculate the density in grams per liter of oxygen gas at STP. You're going to divide the molar mass, which is in grams per mole, by molar volume, which is going to be liters per mole, which is going to be 22.4. And that's dividing the 32 by the 22.4. That makes sense? What's the molar mass of oxygen? Each one's 16, so 32 grams divided by volume, and given the STP conditions, 22.4, gives you that number. All right, and notice the density is going to be in grams per liter, though, because the 22.4 liters has the liter unit. If you wanted it to be in grams per milliliters, which is usually the unit for density, then you would have to convert it. Okay, so when you divide, you get 1.43 grams per liter. The moles of oxygen are common to the denominator and numerator, and they cancel out. And this is only going to be true for STP conditions and no other conditions. Any other questions on this? No questions? Okay, well, let's go back to the e-text then. For this next section, 11.9, we are still going to apply the PV equals nRT equation as needed. So if you are absent, then that's your time to catch up. Okay, so what we're going to do now is calculate the volume or amount of gas in a chemical reaction using ideal gas law. We're going to use mole factors or mole ratios from the balanced equation, and we're going to get, and molar mass, of course, we're going to need to use molar mass. So let's look at this problem. What volume in liters of chlorine gas at 1.2 atmospheres and 27 degrees Celsius is needed to completely react with 1.5 grams of aluminum? So you want to think about what's given over here and what you're looking for. You're looking for the volume of chlorine gas that you would need to react with the mass of aluminum that's given. So how do we go about working on this? Using the information that's given, what can we find? First, to calculate the volume, we can use the PV equals nRT equation. But before we can use the PV equals nRT equation, let's go and write down. You all might want to copy the problem, actually. Go ahead and copy it quickly, and then we can talk about it. So using the pressure that's given and the temperature, we could find the volume if we had the number of moles. And starting with the 1.5 grams of aluminum, we can find the number of moles of chlorine. So let's start working on that. Since you know how to find that, I think I'm going to let you all, based on chapter 9, you can find the number of moles of chlorine that would react with the 1.5 grams of aluminum. So here's the equation. Aluminum plus 3 chlorines gives you aluminum chloride. And you're going to start with the 1.5 grams of aluminum. And then you would go to the equation. What's the mass of aluminum that's reacting in the equation? Does anyone have a periodic table on them?
Yes, it's 27 times 2 is 54.
Okay, so 54 grams of aluminum in the equation. This is the ratio here, is reacting with, since we start with grams, we have to have grams at the bottom. Is going to react with, we're looking for the moles of chlorine. So this quantity of aluminum reacts with 3 moles. We can put mass and moles in the same equation. We talked about that before. So 1.5 times 3 divided by 54. And this gives you 0.083, 0.0833 moles of chlorine. Everybody okay and calculate, understand how to do this? You started with the mass of aluminum that's given, go to the equation, and since you started with grams, you needed to get the mass of aluminum, and that went down over there, and that's the mass of the 2 moles of aluminum. This mass of aluminum reacts with 3 moles of chlorine. And why did we want to put moles of chlorine at the top? Because that's what we're trying to find, moles of chlorine. Once we have moles of chlorine, then we can use this equation. Let's go back to the problem. Pressure given as 1.20 atms. Volume we're trying to find. It said what volume of chlorine gas. And then N is the number of moles. We just found that to be 0.0833. R is the constant, 0.08201, 0.08206. Kelvins times moles. And then temperature is given in Celsius, 27 degrees Celsius. And we would have to add 273 to it. which would give you 300 Kelvin. Okay. Any questions on this page before we go on and start plugging in these numbers into the PV equals nRT equation? Everybody good on this? Okay, so we're going to go ahead. We needed to find the moles from the mole ratio, or the most mass mole ratio, because we needed the N to plug into the PV equals nRT, the ideal gas law equation. So we're going to go ahead now and write your equation down first. Pressure is 1.20 atms. Volume we're trying to find. Number of moles is 0.0833. R is 0.08206 kelvins times moles. Temperature is 300 K. What's next? What do we do next? In order for us to get the volume, what are we going to need to do? This is our unknown variable. This is your x. So you would divide both sides by the 1.20 to try to isolate the x, or the v in this case, atms. This and this cancels. You have 1.20 atms up there. And this is moles, right there, the 0.833 that we calculated. So atms and atms cancels. Kelvin and Kelvin cancels. This is, put mole at the top, so it's this moles and this moles cancel. And we end up with, the only unit that you have left is the liter unit, and that's what we're looking for. We're looking for volume. V is equal to, in liters, now multiply the 0.0833 times the 0.08206 times the 300, divide by the 1.20. 8206 times 300 divided by 1.2, and that gives you 1.71 liters. All right, any questions on this? Kira, do you have any questions since you were out last time?
The only thing is you said the constant,
Mm-hmm.
and
That value is given with the problem. It's like it will be given to you as one in your in the page that has all the given information on there.
Oh, okay.
And that's where it would be.
Oh, okay.
Yes, Latanya.
Where did the R come from? Was it given? Or?
R is part of the equation. You see that right there, right?
Yeah, that's what I was talking
Yeah,
about.
it's part of the formula, and R would be given to you. It's not given to you here in the problem, but normally if this was a problem on the exam, then R would be provided. And because R is a constant, and its value stays the same, and it's going to be provided to you.
Okay, so that's always going to be R.
Yeah,
Okay, so 0.08202.
right.
Okay.
Okay, so let's go now to the e-text and do some work from there. All right, we're going to use Dalton's law of partial pressures to calculate the total pressure of a gas, of a mixture of gases. What does Dalton's law say? Let's go and define what partial pressure is first. The partial pressure of a gas is the pressure of each gas in a mixture. It's the pressure the gas would exert if it were by itself in the container. So if you have a gas that's by itself in one container, or you have 10 different containers with 10 different gases, you put them all together in one container, then the added pressure of all those gases would be the added pressure that you would get if you were to add the individual pressures together. So Dalton's law of partial pressure states that the total pressure depends on the total number of gas particles and not on the types of particles. And it's exerted by a gas mixture is the sum of the partial pressures of those gases. So if you have a gas mixture, the total pressure of that gas mixtures would be the P1, P2, and P3, which would be the individual partial pressures of each of these gases that are in the mixture. Does that make sense? You have 10 different containers, 10 different partial pressures. You put them all together, the total pressure would still be the added pressure of those same individual partial pressures, because pressure depends on the number of particles. And if as long as you have the same number of particles, then the partial pressure exerted will be the same. All right, so you have in these two individual cylinders, you have helium, which is exerting a partial pressure of 2 atmospheres, and then you have argon at a partial pressure of 4 atmospheres. You put them together, and all you have to do is add up the individual partial pressures, and you would get the total pressure of the gas mixture, because all you did was put the particles together. The air you breathe is a mixture of gases. A typical mixture of gases in the air is nitrogen, oxygen, carbon dioxide, argon, and water. So nitrogen, being 78.2% of the gas of air, is going to exert about 78.2% of the total partial pressure, which is the total pressure exerted by air is 760 millimeters of mercury, out of which 594 millimeters of mercury would be exerted by the nitrogen, because that 594 number is 78.2% of the 760. And the oxygen would exert 160 millimeters of mercury, since it's 21% of the total. And then the other trace gases would exert 6 millimeters of mercury, because they make up 0.8% of the total. A scuba tank contains oxygen with a pressure of 0.450 atms and helium at 855 millimeters of mercury. What is the total pressure in millimeters of mercury in the tank? What are we going to need to do so we can add these two individual pressures up?
Convert the helium to ATM.
Right. We would have to either put them both in millimeters of mercury or put them both into ATM, and then we can add them up. So the total pressure would equal to the pressure of oxygen plus the pressure of helium. So we're trying to add the 0.450 atm to the 855 millimeters of mercury, but they're not with the same units, so we're going to have to convert to one or the other. And 855 millimeters of mercury, using the conversion factor 1 atm over 760 millimeters of mercury, would give you 1.12 atms. Once you get the 1.12 atms, you can add it to the 0.45, and you get the total pressure. A gas produced in the lab usually contains water vapor, and the total pressure of that gas would equal to the partial pressure of the water plus the pressure of the gas. Do you all remember collecting the gases that we collected, hydrogen and oxygen, when we made them in the lab? And we collected them over water, and those gases would contain the water component in there. So they would contain the pressure of the gas would be there, and then the pressure of water would also be in there. The gas produced in the lab has a partial pressure obtained by subtracting the vapor pressure of water from the total pressure. So if you are told in a problem that the gas is being collected over water, then you want to get the vapor pressure of water and subtract it from the total pressure of water that's given, and the vapor pressure of water is also usually provided at that temperature. All right, so magnesium reacts with hydrochloric acid, and this is exactly what we did in the lab, if you remember. We had, instead of magnesium, actually, what metal did we use? We had hydrochloric acid in that big test tube. It was sitting in the rack, remember?
Wasn't that little square?
The square piece, exactly.
Zinc, right?
We used zinc. So we put the zinc together with the hydrochloric acid. We had a very similar reaction, and we made hydrogen, and then we collected it in the vial. As the hydrogen gas is produced, it displaces some of the water in the container. The gas collected will be a mixture of hydrogen and water vapor, because it's coming through water. And this is exactly what our apparatus looks like too, right? A square piece, and then goes down the tube, and we collect it with this by the displacement of water. We use the vapor pressure of water at the experimental temperature to determine the amount of dry hydrogen gas produced in the reaction. A gas from a reaction is collected by bubbling through water. Due to evaporation of water, the total pressure is equal to the partial pressure of the gas and the vapor pressure of the water. And we're going to go ahead and use this information to work on a problem. So when magnesium reacts with hydrochloric acid, a volume of 0.355 liters of hydrogen gas is collected over water at 26 degrees Celsius. The vapor pressure of water at 26 degrees Celsius is 25 millimeters of mercury. If the total pressure is 752 millimeters of mercury, how many moles of hydrogen gas were collected? So we have the equation given, we have information given, we're given volume, we have temperature, and then we're given the total pressure, and it says how many moles of hydrogen gas were collected. What do you think we should do? What's the first thing we should do based on what we just went over? If it was collected over water, and especially since you're given the total pressure and then you're given the vapor pressure of water, what would you do first? We would have to subtract the vapor pressure due to water, which is 25 millimeters of mercury, from the total pressure. Then we're going to get the number that we need. The vapor pressure of water at 26 degrees Celsius is 25 millimeters of mercury. We're going to subtract total pressure minus pressure due to water, and you get 727 millimeters of mercury. Is this making sense or no? Okay. And then, now we have the pressure that we need, we have the volume, we have the temperature, and we can start using the PV equals nRT equation. And plugging it into the PV equals nRT equation, we're going to get the 1.38 times the negative second, or moles of hydrogen. Does that make sense? We've done many of these before, so hopefully nobody wants me to put this in there again. Or do you all want to go and do this part? You know how to do it, right? Okay. All right, so let's go ahead now and do some problems from the overhead. I mean, from the textbook.